A camera had never reached the bottom of one of America's most iconic lakes. Scientists had studied its surface for decades without anyone descending to its true floor, 1,570 feet down. Then a small nonprofit built a robot in a garage, on a fraction of any real research budget, and sent it into total darkness anyway on September 5, 2025. What the cameras sent back was not what anyone expected to find. The lake that defies basic logic, Lake Tahoe, sits on the border of California and Nevada, straddling the Sierra Nevada mountains at an elevation of 6,225 feet above sea level. From the shore, it looks like every other alpine lake, blue and cold and framed by pine trees and mountain ridges. The numbers tell a different story. The lake covers 191 square miles of surface area, runs 22 miles long and 12 miles wide, and at its deepest point plunges 1,645 feet straight down into the earth. That makes it the second deepest lake in the United States, surpassed only by Crater Lake in Oregon, and one of the deepest lakes in the world. To understand how deep 1,645 feet actually is, consider that the Eiffel Tower stands 1,083 feet tall. You could submerge it completely, and still have 562 feet of water above its tip. The bottom of the lake sits 92 feet below the elevation of Carson City, Nevada, which is miles away on the other side of the mountains. The lake holds roughly 36.2 trillion gallons of water, a volume large enough to cover the entire state of California, to a depth of 14 inches. This depth is not a geological accident. It is the product of tectonic forces that began reshaping this region roughly 3 to 5 million years ago, when the valley that would become the Tahoe Basin began sinking between two parallel fault lines as the mountains on either side continued to rise. The Sierra Nevada block lifted to the west, the Carson Range lifted to the east, and the central block subsided between them, forming a deep structural trough called a graben. As the mountains rose and the valley dropped, rivers and snowmelt began filling the resulting basin. Then, roughly 2 to 3 million years ago, a series of volcanic eruptions from a volcano called Mount Pluto on the lake's north shore sent lava flows that blocked the basin's natural outlet and forced the water level to rise hundreds of feet higher than it sits today. Eventually, the lake eroded down to its current outlet at Tahoe City, where a dam now controls the water level. Additional glacial activity between roughly 1 million and 20,000 years ago carved and reshaped the western shore, leaving the deeply sculpted topography that includes features like Emerald Bay. The result is a lake that has remained remarkably stable in size and character for roughly 1 million years, holding water that may have entered the lake before European contact with the Americas, and sitting in a basin shaped by forces that began operating when the first recognizable hominins were emerging in Africa. Why the bottom stayed dark for so long? Lake Tahoe's extraordinary depth creates conditions that make its deepest zones genuinely difficult to study. The practical challenge is straightforward. Getting equipment to the deepest point requires a tether or cable nearly 1,700 feet long, handling pressures that destroy ordinary electronics, and navigating a pitch-black environment where the lake's famous surface clarity provides no advantage whatsoever. At the surface, Lake Tahoe is legendary for its transparency. In the 1960s, a white disk lowered into the water on a measuring line remained visible to the naked eye at depths beyond 100 feet, a transparency reading that put the lake among the clearest large bodies of freshwater on the planet. That reading has since declined to around 60 to 70 feet as of 2025, still extraordinary by global standards, but a significant loss from historical levels. None of that surface clarity matters once you descend past a few hundred feet, because sunlight does not penetrate anywhere near the bottom. The deepest zones of Lake Tahoe exist in permanent, complete darkness, similar in that respect to the deep ocean, except that this is a freshwater lake in the Sierra Nevada rather than a saltwater basin in the Pacific. The water temperature at those depths stays close to 39 degrees Fahrenheit year-round, the temperature at which fresh water reaches its maximum density. This thermal stability means the cold, dense deep water almost never mixes with the warmer water above it. UC Davis researchers monitoring the lake since 1968 note that Tahoe's full-depth mixing, when surface water cools enough in winter to sink all the way to the bottom, carries oxygen and nutrients downward, and happens only in certain conditions. During exceptionally cold winters it occurs. During warmer years it does not. As average temperatures have risen by roughly 1.4 degrees Fahrenheit since 1970, this critical mixing has become less reliable, with consequences for the oxygen content of deep water and the organisms that depend on it. The myths that grew around the unseen depths were entirely predictable. The most persistent legend holds that Jacques Cousteau explored the lake in a submersible sometime in the 1970s, emerged visibly shaken, and refused to describe what he had seen, saying the world was not ready for what was down there. There is no evidence Cousteau ever visited Lake Tahoe. The story appears to have circulated for decades without any documentary basis. A second enduring myth holds that the cold, deep water has preserved the bodies of organized crime victims from the casino era of the mid-20th century, perfectly intact at the bottom, never decomposing because the water is too cold for the bacteria that would normally break them down. This claim has no confirmed factual foundation either. Cold water does slow decomposition, but bodies do not indefinitely persist as myths describe. No confirmed evidence of such remains has ever been produced. For a very long time, no one had actually looked. The first camera to reach the bottom. On the evening of September 5, 2025, a remotely operated vehicle called Deep Emerald descended through the darkness of Lake Tahoe until its wheels touched the lake bed, nearly 1,600 feet below the surface. It was the first time any camera, manned or unmanned, had ever recorded footage from the lake's deepest zone, and more than 3,500 people watched it happen in real time through a live stream broadcast by the Tahoe Fund. Deep Emerald was built specifically for this mission by the Restoring the Lake Depths Foundation, led by its founder and executive director Lindsay Kopf. The ROV uses open-source electronics from Blue Robotics and Mission Robotics, has 8 thrusters, carries extremely powerful LED lights capable of illuminating the otherwise total darkness of the lake bed, and is equipped with a 4K camera capable of capturing fine detail in environments devoid of any ambient light. It connects to the surface through a 1,960-foot fiber optic tether rather than the copper cable used in conventional ROV systems, a specific engineering choice that allows for higher resolution video, better data feedback, and the depth capability the mission required. Tim Crandall, president of Seaview Systems, which helped modify the vehicle, noted that the fiber optic system was essential for reaching the depths the team intended to explore. The total cost of building Deep Emerald was approximately $50,000. Kopf deployed the vehicle from a position roughly in the middle of the lake, slightly south of Tahoe City, in one of the deepest sections. Over the course of a 12-minute deployment on the lake bed, the ROV traveled approximately 400 to 500 meters across the bottom, sending back continuous 4K footage to the researchers on the surface. Sudeep Chandra, a foundation professor of limnology at the University of Nevada, Reno, who participated in the live stream, compared the significance of exploring the deep lake zones to understanding the lake's lungs, essential for the overall health and functioning of the entire ecosystem. What the camera showed was simultaneously quieter and more scientifically informative than any legend about the lake had predicted. What the cameras actually found, the lake bed in the deep zones of Lake Tahoe, is a world of fine sediment and near-total stillness. The camera footage from Deep Emerald showed a surface covered in soft, pale silt, undisturbed by the currents and boat traffic affecting shallower sections. The ROV's powerful LED lights illuminated what researchers described as a starfield-like pattern of particles floating just above the bottom, fine material that had not fully settled, drifting slowly above the silt. Chandra called what the camera was moving through flocculent material, a mixture of dead algae, organic matter, inorganic particles, and fine sediment that settles gradually from the waters above. This same material, while still suspended in the water column, is what scatters light and reduces the lake's famous clarity. Watching it accumulate at the bottom gave researchers a direct visual of the process driving Tahoe's long-term transparency problem. The team also observed what appeared to be mysid shrimp along the lake bed. These tiny crustaceans, each less than an inch long, make one of the most remarkable daily migrations of any freshwater organism. Every night, billions of them ascend hundreds of feet from the dark bottom to feed at the surface. Every morning, they descend again to escape fish that hunt by sight. In the deepest sections, that round trip covers nearly 2,000 vertical feet every single day. What the cameras did not find was equally significant. No monsters, no preserved bodies, no evidence of the legends that have circulated for generations. What was there instead was stranger and more consequential, a quiet, cold, dark environment holding direct clues about the lake's health that no one had ever been able to observe before. The accident that changed the lake forever. The mysid shrimp performing their nightly migration were not always part of this lake. Between 1963 and 1965, the California and Nevada Departments of Fish and Game deliberately introduced them, known scientifically as Mysis diluviana, into Lake Tahoe and Emerald Bay. The reasoning seemed sound. Lake trout were the primary sport fish, and a plentiful shrimp population seemed like a reliable way to increase their size and survival. Similar introductions in other western lakes had appeared to work. Lake Tahoe went the other way. The shrimp population established itself by 1971 and exploded. Within 8 years of the first introduction, two of the lake's most productive native zooplankton species, Daphnia and Bosmina, had essentially disappeared. Those zooplankton had been doing critical work, consuming algae and fine particles that would otherwise stay suspended in the water and reduce transparency. When they vanished, that natural filtration stopped. The lake trout the shrimp were meant to feed did not benefit. Lake trout hunt by sight, and the shrimp spend their days in dark, deep water, making them largely unavailable. The shrimp instead outcompeted the juvenile fish for food. The trout grew smaller, the lake grew cloudier. A straightforward management decision cascaded through the food web in ways nobody anticipated, and those effects are still running through the system more than 60 years later. UC Davis researchers are now investigating whether controlled removal of mysid shrimp from specific areas could restore the zooplankton and recover some of the lost clarity, using Emerald Bay as a test site. What the legends got wrong and why it matters. The mythology surrounding Lake Tahoe's depths has persisted in part because no one had footage to replace it with. The Cousteau story, despite having no factual basis, circulated for decades precisely because there was no visual evidence from the deep lake to contradict it. The perfectly preserved bodies of mob victims, which cold water would slow but not indefinitely prevent from decomposing, became cultural fixtures around casino-era Tahoe because the bottom was inaccessible and therefore mysterious. Caroline Grossman, from the Restoring the Lake Depths Foundation, addressed the body question directly during the September 2025 livestream. The answer is no. That is a myth. What the camera found on the lakebed was silt, flocculent material, and evidence of a complex and stressed ecosystem, not crime scene evidence preserved by the cold. The reason this matters is not just factual correction for its own sake. The myths about the lake's depths have shaped how the public thinks about what lies below the surface and whether it requires attention. A lake believed to hide preserved bodies and unknown monsters is a lake perceived as capable of looking after itself, mysterious, and self-sufficient. A lake whose bottom is covered in fine sediment accumulating from development runoff, whose clarity has declined by a third since careful monitoring began, whose deep water mixing is becoming less reliable as temperatures rise, and whose food web was restructured by a 1960s management mistake that set off 6 decades of cascading consequences, is a lake that requires active and sustained human attention to maintain. The footage from Deep Emerald does not make Lake Tahoe less interesting. It makes it more so, and in a way that carries direct implications for the people who live around it, visit it, and depend on it. The sediment record nobody knew was there. One of the findings generating the most scientific discussion was the visible condition of the fine sediment layer on the lakebed. Because the deepest zones of Lake Tahoe experience essentially no physical disturbance, no currents strong enough to stir the bottom, no burrowing organisms disrupting the layering, sediment there accumulates in undisturbed horizontal strata. Each layer represents a different period of time, and the materials within each layer preserve the chemical signatures of what was happening when that sediment was deposited. Pollen grains indicate what vegetation surrounded the lake. Charcoal marks fire years. Algae remains reflect shifts in water chemistry. Mineral composition tracks changes in watershed runoff. The sediment record at the bottom extends far beyond the surface monitoring dataset UC Davis has maintained since 1968, itself one of the longest freshwater records in the world. Submerged tree stumps found in shallower sections of Lake Tahoe and in nearby Fallen Leaf Lake have been radiocarbon dated to between 4,800 and 6,300 years old, from a period when a prolonged drought dropped the lake level enough to allow forest growth along what is now the lakebed. Some trees at Fallen Leaf Lake date to a medieval megadrought lasting 150 to 200 years between the 9th and 12th centuries, with trees still standing upright at depths up to 77 feet. What Deep Emerald captured on camera was the top of that archive, the most recent layers of a geological document extending thousands of years back, undisturbed and almost entirely unread. If that kind of record is what keeps you watching, subscribing is how you make sure the next chapter of this story reaches you. The pollution finding nobody wanted Deep Emerald was not the first camera to find things at the bottom of Lake Tahoe that should not be there. A study published in Applied Spectroscopy in late 2023 by researchers from the Desert Research Institute and the UC Davis Tahoe Environmental Research Center, working with the nonprofit Clean Up the Lake, sent scuba divers along 9.3 kilometers of lakebed near Lake Tahoe Nevada State Park and Zephyr Cove. In just that small fraction of the lake, divers counted 673 plastic items, averaging 83 pieces per kilometer. Near Hidden Beach and South Sand Harbor, the density reached 140 and 124 pieces per kilometer respectively. Not one stretch of the surveyed lakebed was entirely free of plastic. Cleanup the Lake had already completed a 72-mile scuba cleanup of the lake's entire circumference in 2022, and removed more than 69,000 pounds of litter from beneath the surface of Lake Tahoe and surrounding alpine lakes. The 2023 study showed the work was far from finished. Plastic continues reaching the bottom faster than cleanup efforts can remove it. That study covered shallower zones accessible to divers. Deep Emerald's footage came from nearly 1,600 feet down, a depth no diver can reach. Whether the same plastic accumulation extends to the deepest zones is not yet confirmed, but researchers consider it likely. Surface plastic sinks regardless of how deep the water beneath it is, and there is nothing at those depths to stop it from settling. What climate change is doing to the deep? The deep water of Lake Tahoe is not isolated from the changes happening at the surface. UC Davis has been tracking the lake's response to climate change through continuous monitoring since 1968, and the data shows clear and accelerating trends. Average air temperatures in the Tahoe Basin have risen significantly over the past century. The average daily minimum temperature has increased by 4.2 degrees Fahrenheit and is now above freezing, which means that the number of days cold enough to produce significant snowfall rather than rain has declined. Snowpack in the Sierra Nevada, which supplies a large portion of the water that replenishes the lake, has been decreasing as a proportion of total precipitation since 1910. Average lake water temperature has increased by approximately 1.4 degrees Fahrenheit since 1970. The warming has direct consequences for the lake's deep water dynamics. Each winter, when surface water cools enough to become denser than the water below it, it sinks, mixing downward and carrying dissolved oxygen into depths where no photosynthesis occurs, and oxygen can only arrive by this mixing process. This annual deep mixing is how the lake's deep water stays oxygenated enough to support life. As warming reduces the frequency and depth of this mixing, deep water oxygen levels become a concern for the organisms living in those zones. Lake Tahoe currently mixes to its full depth on average only once every 4 years. During exceptionally cold winters with significant snow, mixing reaches all 1,645 feet. During warmer, drier years, mixing may not reach the deep zones at all. UC Davis researchers have noted that since 2012, the lake has been warming at a record rate. And if that kind of data is what keeps you watching, subscribing is how you make sure the next update reaches you before it gets buried. If that trajectory continues, the periods between complete deep mixing will lengthen, and the deep water zones will become progressively more oxygen-depleting names. The warming also affects the invasive mysid shrimp situation. Warmer surface water extends the productive season for algae growth, providing more food at the surface during more of the year, which increases the shrimp population's opportunities to exploit that food source. A larger mysid population consumes more zooplankton. More zooplankton consumption means less natural filtering of the water column. The clarity declines further. Each component of the problem is connected to the others in ways that make single-cause solutions inadequate. What the dive means for what comes next. The September 2025 dive by Deep Emerald was not a conclusion. It was the first sentence of a much longer investigation that has barely begun. COF and the Restoring the Lake Depths Foundation are planning continued expeditions to the deep lake, with the goal of building the kind of systematic visual and scientific record of the deep zones that has existed for the lake's surface since 1968, but has never existed for the depths. Future work with the ROV will focus on several specific questions. How does the flocculent material visible in the 2025 footage relate to the broader clarity problem? What organisms are actually present at different depths, and how do their populations change seasonally and over time? What does the undisturbed sediment record at the deepest point contain? And can cores from those zones extend the scientific record of the lake's history further back than existing data reaches? Are there specific zones or features of the lakebed that are more scientifically significant than others and deserve focused investigation? Chase Petley, an independent ROV operator and offshore underwater ROV pilot, who has been exploring Lake Tahoe's depths through his own self-funded expeditions for more than a decade, has built more than 15 different ROV systems in pursuit of these same questions. Petley's cameras have found fish at depths where scientists said fish would not be found, old boats without registration numbers whose age he cannot determine, and persistent evidence of a lake whose depths are far more inhabited and biologically active than the conventional scientific understanding had predicted. He has described the lake's bottom as something that continues to surprise anyone who actually goes there with a camera, and said he is committed to continuing the exploration because the answers to the questions he keeps finding are themselves generating new questions. The 4K footage from the September 2025 dive will be used by Chandra and his colleagues at the University of Nevada, Reno, to support further studies of the lake's underwater ecosystems and water clarity, and to inform environmental monitoring and management decisions that affect the lake's future. Verdict here is what the evidence shows. Lake Tahoe sits at 6,225 feet elevation on the California-Nevada border, runs 22 miles long and 12 miles wide, and reaches a maximum depth of 1,645 feet, making it the second deepest lake in the United States. It formed between 3 and 5 million years ago as the central basin subsided between parallel fault lines and later filled with water, with volcanic activity blocking its outlet roughly 2 to 3 million years ago. Its surface clarity, which measured beyond 100 feet in the 1960s, has declined to approximately 60 to 70 feet due to fine sediment, algae growth fueled by development runoff, and the loss of native zooplankton that once filtered the water. Average lake water temperature has risen 1.4 degrees Fahrenheit since 1970. Invasive mysid shrimp, introduced by the California and Nevada wildlife agencies between 1963 and 1965, destroyed the native zooplankton populations within 8 years of introduction and restructured the lake's food web in ways that continue to reduce clarity and affect native fish species. On September 5, 2025, the ROV Deep Emerald, built by the Restoring the Lake Depths Foundation with support from the Tahoe Fund and Martis Camp Foundation, descended nearly 1,600 feet to the lake bed under a live stream watched by more than 3,500 people, recording the first ever 4K footage from the lake's deepest zone. The camera found a dark, still world of fine silt and flocculent material in patterns that limnologist Sudeep Chandra compared to a star field, evidence of the sediment accumulation driving the lake's clarity loss visible in the most undisturbed part of the system. Mysid shrimp were observed living at depth. Fish were absent at the deepest zone. No evidence was found supporting legends about preserved bodies or unknown creatures. A 2023-2024 dive survey published in Applied Spectroscopy by researchers from the Desert Research Institute and UC Davis found 673 plastic items in just 9.3 kilometers of shallower lakebed, averaging 83 pieces per kilometer with no surveyed section entirely free of plastic. The nonprofit Clean Up the Lake has removed more than 69,000 pounds of litter from beneath the surface of Lake Tahoe and surrounding alpine lakes since 2018. The deep lake is not empty, it is not pristine, and it is not the realm of monsters and organized crime preserved in ice that the legends describe. What it contains is a complex, cold, dark, stressed ecosystem whose history goes back thousands of years and whose future depends on decisions being made right now about development, warming, invasive species, and plastic reduction. The cameras finally got there. What they found is the beginning of understanding, not the end of mystery. If this is the kind of story that keeps you watching, subscribing means the next one finds you.